So welcome everybody to this session of the UruCon 2021 Congress. The next session is called a coplanar waveguide fed Metasurface multiband antenna with Aperture coupling, and the presenter will be Lalit, Reddy, Muthyala, with the co-authors Chilukuri, Sulakshana, and Meghana, Anumula. And excuse me for the pronunciation of your names. Perhaps you can pronounce your names as they should be. So go ahead, you can share your screen and start the presentation. Remember that you will have 15 minutes for the full presentation.
Okay, thank you so much. Thank you so much, sir. Thank you so much. Greetings, everyone. Just give me a minute. I'll just share my screen. Hi, sir. Greetings, everyone. I'm Lalit. I'm currently in Vardhaman College of Engineering. So actually, our project is a CPW fed aperture coupled Metasurface antenna. So I am Lalit. I'm the presenter, and some of our colleagues are Sulakshana, Chilukuri, and Meghana, Anumula. We are from the Department of Electronics and Communication Engineering from Vardhaman College of Engineering, Shamshabad, Hyderabad. So basically, let's come to the outline. We have an agenda to how the everything is going place. First, let me start with the problem and motivation, and then with the objectives, and then with the introduction of a few of the topics, and then let's study the literature papers which we have taken a glance to while coming to the conclusion, and then let's go to the antenna structure followed by the conclusion. So first, what was the problem? We know that there are so many antennas which give wide bandwidths, but we just want one antenna which will give a good bandwidth, which is of various frequencies, so that we can have multiple bands at the same particular desired frequencies. So that is the reason we have chose this type of antenna. So our objective is, what is our objective? So basically our objective is to try to enhance the bandwidth at that particular frequencies which we are desired by using the properties which are exhibited by the materials which we have used. So for example, in our case, we have used meta surface materials which are artificial in nature, so that through which the speciality of meta surface is it will improve the gain bandwidth product, and also it will suppress the backward radiation. And also by using this, we can also get the bandwidth impedance matching at lower frequencies as well. So coming to the we were discussing about the same here. This is the meta surfaces. These are the particles which we can see. This is what we usually have the structure about. So these are the loads which we can see. And coming to its disadvantages, difficult, when we are trying to do or fabricate it, it is a bit difficult, because they are artificial in nature, and they have their over cohesiveness, and also the losses which they have are very huge. So that is the reason there will be a bit difficulty in fabricating it. So coming to the microstrip antennas, like we are all familiar with what is microstrip antennas, right? So basically microstrip antennas, they're widely used in modern wireless technologies, or communications, which also have disadvantages such as narrow bandwidth and all. Despite all these disadvantages, let's focus on the advantages. It has a compact configuration, it is lightweighted, it has a good conformability, so that it can be placed at any structures or bench structures, or any it can also be used as conformal antennas. And all these are the the unique properties or the advantages of microstrip antennas. So to enhance the bandwidth, coming to enhance the bandwidth also, one more the technique which we are using is Cpw feeding. So what happened is, here in this feeding technique, the where we are using a microstrip antenna, here the signal and the ground currents are etched on the same layer. But in other cases it is not done like this. But in while doing this CPW feeding, here both the signal as well as the ground will be etched on the same layer, that is the ground layer. Due to this, what will happen is it will have actually produce the high bandwidth, and also the losses which are there at the lower frequencies will be lesser when we are compared to the microstrip feeding. We have different feeding techniques, right? So when we compare with the microstrip feeding, here the losses will be a bit lower. As it also has a negative point, that is a disadvantage, that is it has a lower gain comparative to other feeding techniques. So here we are also using the aperture coupling technique to feeding the patch. So here there are three layers, right? So the first layer is the patch, and the second layer is the ground, and then below that we are keeping a feeding substrate. So here this is the feeding substrate which we are doing. So here what will happen is the ground and the feeding substrate will have the same etching. So that is what we are doing here. So basically here what happens is it allows the planar feeding, and we can use different types of substrates here. As it also has a few disadvantages, to name a few. It has multi-layer fabrication it will require, like which is different. So coming to the literature view, so basically here what we have done is before performing the project, we have also seen different papers which were existing before. Let's have a review of two of them. So basically, first paper where we have low profile wideband metasurface antenna using characteristics mode analysis. So characteristics mode analysis is one of the technique through which they have tried and found the bandwidth. So here we can see the configuration of various metasurfaces. Here also they have used the metasurfaces with the top slot, right? So here we can see the structure of it, which is rhombus in structure, and the modal significance and the frequency graph is given below with the different modes. Through this, we have got 31% bandwidth, and also here we have less gain. So that is the reason we have not taken this. So this is the disadvantage of this. So getting on to the next literature paper. So the next literature paper is metamaterial based low profile broadband mushroom antenna. So here what happened is, here in this type of mushroom antenna, here we have the structure. It is a 16 cell structure which is arranged in a 4x4 dielectric filled mushroom. So here there are four, right? This 1 2 3 4, this is one slot. 1 2 3 4, this is one more slot. In this kind of way, it is a 4x4. So this is 1, this is 2, this is 3, this is 4. Here we have a good bandwidth, or we have a good gain, because here feeding slot is down, and also the mushroom cells are on the patch inside, and on the ground plane side. So here the thickness is also very low, that is 0.060 lambda. But the disadvantage we are seeing here is the bandwidth is very low, that is 25%. So here by having the literature review, we can see that we are when we have good bandwidth, we are not having gain. When we have good gain, we are not having good bandwidth. So that is the reason we have found we have tried to find out one antenna which is having good bandwidth, or good bandwidth, and also which can resonate at multiple frequencies, so that it is not only used for one purpose but also for multi purposes, right? Because one antenna should not be restricted to doing one thing or another thing. Let's see what we have done. So to study the proposed antenna, or to come to conclusion of how to do the proposed antenna, we have seen the base 5 antennas. The process goes like this. So in the first antenna, we have a rectangular or a square patch which is etched, and here in the bottom we have an L-shaped edge, so that this is the structure with the geometrical dimensions as shown below. Here to the left down corner we have the HFS's geometrical structure which is drawn. So here what happens is, here while coming to this antenna, as there is only one patch, there is no much difference, and the bottom is all the ground structure is also a L-shaped one. And the next one what we have done is, because it is because of what it we have done is, so in the second thing we have kept the bottom as it is, so the bottom view is the same. But for the patch, what we have done is, we have tried changing one patch to another patch which are of equal size. Now here the patch is the same of as that of the square patch which we used in the earlier antenna. It is the same, but this we have break down into 9 patches with the geometrical dimensions, and but the bottom view remains the same. In the next antenna we have tried increasing the size or the geometry of the middle antenna, which is directly below above which is directly above the L-shaped structure, where the bottom view remains the same. In the next antenna what we have done is, we have the antenna of the third, right? The top view remains the same after this, and now we have tried changing the bottom views. Till now what we have done, we have changed the patches, but now we have just tried limiting not only to the patch but also to the ground. So the changes are now observed in the ground structure itself. Now here what we have done is, here we have given a staircase structure where we can get a good impedance matching with its bandwidth here. So here we have L2, which is the uppercase, and which we have the lowercase. So here we have a staircase structure beneath this only, beneath this middle row only. So the next antenna we have added with the same structure as the fourth, just some modification which is done here is, we have etched these parts. These parts are etched. That is the final, the 4 pieces of this, here too and here too, with the same geometrical dimensions. So what is that we are why are we changing all these? So basically after changing each of the antenna, these are the results which we have observed. So basically the first antenna, which is a square patch antenna, here we are this which is a square patch, only a single antenna. This one, it is having a, so it is having a very less reflection coefficient, but hence after doing this the reflection coefficient is changing, and also we are getting it at multiple points. So these are all the existing which we have done. So what have we created new, which is the proposed antenna? This is the top view of the proposed antenna, and this is the bottom view of the proposed antenna. Here we have not made much changes with the bottom view, but we have significant changes with the top view, that is the patch. Here we have changed altogether the patch antenna structure from square to it being a annular structure, because of our desired frequencies are different. Here it is for wideband or it is for other bands, this usage of this, but here we want for multi-band frequencies. We are seeing not only for we desire for one frequency but for another frequency. So these are the reflection coefficient characteristics which we are observing here. Beneath -10 we have got good reflection coefficients, as well as we have different 5 different 1, 2, 3 and 4 and 5 which are lower than -10 dB. So which makes our objective more clearer, and also here our problem is solved. To solve our problem, and also we have observed the radiation patterns here, which are E planes and H planes, at various frequencies, because our antenna is not only limited to one frequency. We have a pentaband frequencies that is at 2.42 gigahertz, at 2.86 gigahertz, at 6.99 gigahertz, at 6.29 gigahertz, and at 7.96 gigahertz. So at 5 frequencies we have different E planes and H planes, which are as shown. And what are the uses we have done for 5 bands, but what are the uses for this? So let's coming for the uses. Here we can use it at Wi-Fi frequencies or cordless phones frequencies or WLAN frequencies. You can use it for communication, that is whether it can be radar applications or satellite communications or civil aviations at 2.8 gigahertz, or for satellite televisions of S-band, or for C-band communication satellites. These are all the frequencies or the different bands in which our antenna can resonate perfectly at good bandwidths. So yes, these are a few references which we have taken from it. And yes, thank you so much, sir.
Okay, thank you very much, Lalit. If someone has questions, you can write down the questions in the chat session or in the Q&A section of the chat. It seems that there are no questions at this time, so thank you very much, Lalit, for you and for your team.
Thank you so much, sir.